in exercise 3, we want to find some approximation of the ruin probability on a finite time interval. And we call this approximation the Arfwedson approximation. Now, what is the setup in exercise 3? Well, you assume you have a company where the initial capital is U. Furthermore, we assume that the capital growth is measured once per time unit, so is discrete, and is discrete in time, and increments by xi, which is normally distributed with mean value 1 and variance 1, where we also assume that the increments are IID, so they're independent of each other and also identically distributed. Then the total capital growth from time 0 to n is given by Sn equal to x1 plus x2 plus etc. up until xn. How do we define the event of ruin? Well, note that ruin occurs if and only if Sn goes below minus u, because that means the change in capital has eaten up all of our initial capital. What is it that we want to look at in this exercise? Well, the thing that we want to consider is the probability of ruin on some finite time intervals. So we would like to consider the probability of ruin, so the probability that, oh, there should be a minus here, the probability that Sn is smaller than or equal to minus u for some n that is smaller than a number. And that number we write as delta multiplied by u. And that seems a bit weird just at first, but it turns out that it's easier to calculate this finite time ruin probability if the boundary on time is given by delta u as compared to if it's just given by some arbitrary fixed number. So what we mean by delta u is that delta is a positive but small number, while u is indeed just the initial capital. And we denote this probability by psi delta u. And what we're going to do is not that we're going to calculate this thing, but we would actually just like to consider this thing and find an upper bound for it. So that is what we are going to do in B. Just before we finish this video, I would like to note that in A, we are asked to find the cumulant generating function, which is defined as the logarithm of the moment generating function of x1, where x1 is one of these increments. And in A, the calculation of this cumulant generating function is something that we will not do on video because you've actually already calculated it in exercise 1A, I think, or It's either 1a or 2a. But in one of the first exercises, in the first exercise set, you actually showed exactly that the cumulant generating function is alpha plus alpha squared halves. So we're not going to go through that calculation. So see you in the next video where we just start directly with b.